Thank you very much, Fred. Now, thanks for the kind introduction as well. So one thing I will point out from the start is this webinar involves me sharing a screen, and sometimes webinars don't do a really good job at transferring the animation, let's say, in real time. So there may be a little bit of jerkiness in this presentation, but we do have some key videos that you can obtain from the Ascendo Reliability website if you are interested in a couple of the cooler ones. And of course, as you can see in Adobe Connect, you should be able to identify that you can download the slides should you want to do that. So without further ado, obviously the name of this webinar sort of gives it away. But before we do, we're going to look at a particular organisation, and more importantly, we're going to start with a story about that organisation. And this organisation in particular, most of you will know who this is. You won't know it until I reveal who it is at the end, but when I do, you'll be very familiar with what it is they do and what products they make. But this company or this organisation had every conceivable quality and reliability certificate and certification that you could possibly hope to imagine. And they, as a result, were fairly comfortable that they were, let's call it, industry best practice. Why would you change anything? Why would you think anything else if you've got every belt, every ISO 1 million certification, every medal, every award? If you get those awards, why would you think that you're anything but the best? Well, the CEO, he had a hunch, and he thought that at the time things weren't as good as all these certificates and all these awards suggested. Now, he launched an investigation, and to his horror, the first thing he found out was that of his manufacturing resources, only 75% of them were being dedicated to manufacturing. And why? Because 25% of his manufacturing resources are being dedicated to defects. Now, this is the cost of failure before it leaves the production facility, let alone the cost of failure associated with warranty and lost customers. So he was obviously quite perturbed by this level of wastage or inefficiency, or this, let's be blunt, failure, given that his company was receiving all these awards. And no one knew about these defects. No one knew that they were a thing. So he and his management team decided to do something about it. What did they do? Well, what they did was provide absolute commitment to improving the situation. And they set a goal, and some of you may have already heard of this goal, which might betray which organisation we're talking about, which is a 10-fold factor decrease in failure rate over a 10-year period. Now, this organisation manufactures and sells consumer products and goods. So in this case, failure rate is not the textbook definition of failure rate. They defined failure rate as a percentage of things that were failing during warranty period. So again, not textbook, but you know what? It doesn't matter if it makes sense for that organisation. And if we were to graphically represent this goal with respect to time, you can see that if we normalize it and start with 100% being where we are at now, this red line represents an exponential decrease over time until we reduce failure rate by a factor of 10. And their project didn't quite get there. The blue line represents how they actually went in terms of reducing the failure rate, and they got to 12.6%. So I suppose technically it was a failure, but in terms of what they were trying to achieve at the highest level, it was a resounding success. They drastically reduced the failure rates they are experiencing in their products. Now, if we look at it in terms of a metric that matters even more, perhaps, this blue line represents how much warranty cost them over the same period, the same 10-year period. And you'll see on the vertical axis, warranty cost is expressed in terms of millions of dollars per year, hundreds of millions of dollars per year. So if they didn't change their failure rates, this is what the warranty cost would have been. You can see it's considerably higher. And the difference, essentially, or the integration of the area, means that they saved $808 million. And that was only in warranty costs. It was almost dwarfed in many cases by the savings they could make on warehousing, because they didn't need to have as many repair parts. They didn't need to do as much testing because the parts were so reliable, so on and so forth. So who was this company? This company was Hewlett-Packard. And the project we're talking about was the 10X project. And it is somewhat well known in the field of reliability engineering, but this is a company whose marketing plan relies on the perception of reliability. And this organization, even though they were perceived to be doing very well at the start because they had all these awards and certificates, when it came to measuring how well they were doing, unfortunately, they weren't doing as well as they thought. So just a bit about me. I'm a reliability engineer, and I work in logistics as well. I work with Fred at FMS Reliability in one of my roles, and also work at QoS Reliability as well. And I have a military background. I was in the Australian Army for about 17 years, where I was a senior reliability engineer in that organisation before I left. I've been a consultant. I worked at UCLA, and I helped set up the Centre for the Safety and Reliability of Autonomous Systems and a few other things. And I suppose my background means that I've been exposed to, let's just say, sometimes overly and sometimes underly technical cultures, where we focus too much on trying to get to a particular root cause in terms of we focus on the science and not the business merits, and sometimes we go the other way where we don't focus enough. We try and make really basic assumptions, and one of those assumptions we're going to talk about today. But before we do that, let's talk about what reliability is. Reliability is a probability that a system has not failed in designated conditions at a particular usage duration. So there are 4 parts to this definition which are being highlighted now. You cannot ever express reliability in any other way besides these you can't have a definition of reliability without these 4 tenets. The first one being a probability, the second one being what failure is, the inability to do some sort of function. We also need to talk about the conditions they're operating in, and usage duration, which is not always time. It tends to be how the equipment or system ages. It could be cycles, it could be distance. So the next question we need to ask is, what is the mean time between failure? We just talked about reliability, and many people, when they think of reliability, they think instantly of MTBF. But what is it? Well, the mean is an arithmetic average or expected value. It is a central or typical value of a set of points or data values. Time, in this case, we just talked about duration and the definition of reliability. So when we're talking mean time between failure, what we actually mean is the usage duration in terms of distance, cycles, engine hours, so on and so forth. Between, that should be obvious. It's not a failure-free period. It implies that there is a repeating process of repair. And the last thing is failure, where the system ceases to function inherently. So if we put these parts together, we now know that the mean time between failure is simply the arithmetic average duration between successive failures of repairable systems. Okay, so what does this mean? Well, tends to mean not a lot. So the MTBF, to expand on that topic, we're going to look at the MTBF in greater detail, which is sometimes denoted with the Greek letter theta. If we want to estimate the MTBF, we can look at field data or test data or anything like that, and we simply divide the usage duration by the total number of failures. And you'll note we have this squiggly equals sign here because it's an approximation. Why is it approximation? Because failure is a random process, and we only ever observe data that is random. So while we can increase our accuracy or improve our understanding of the MTBF by having more data, which means more duration and more failures, we are still only ever going to be able to estimate what the true MTBF of a system is. So let's look at that in a very practical context, such as doing a reliability demonstration test. And we're going to test this truck. And we're going to test this truck over a usage profile, which is, as discussed, not always time. It could be hours, miles, cycles, or however what the best metric is in terms of how this system degrades with respect to time or with respect to usage. So in this test, we're going to drive our truck over 100 hours or miles or cycles, and we observe some failures. And these red dots represent a failure. Now, if we count them, we will see that there are a total of 8 failures, which means we substitute that into our equation to work out that the mean time between failure is approximately 12.5. Well, is that useful? Yes and no. Because if you tell me the MTBF and nothing else, it says nothing to me as a reliability engineer about whether failure is occurring, increasing, decreasing, or staying the same. And why is that important? Well, we want to be able to see this particular trend here. So what you should be able to see on the screen now is how we have a different test result or test outcome where we have those 8 failures. They almost look like they're squished or squashed to the right. And what that suggests to me, at least, is that if we see a failure pattern like this, we could reasonably conclude that this system is wearing out. That is, failures are becoming more and more prevalent or more frequent as the system gets older, which is a classic wear-out tendency. Now, if we squish these all to the left, these failures now look like they're occurring relatively frequently at the start, but they're becoming less and less frequent over time or usage. And this seems to me to suggest that this system might be wearing in. And that's different to wear out, obviously. And the reason I want to know this is because I'm a reliability engineer. I'm not here to admire a problem, which is to do testing, do analysis, write a report, and nothing else. If you just do those things, all you're doing is documenting what the system is as of today. If you don't do anything with this, or if none of this stuff is able to influence design, then you are doing nothing more than admiring a problem or reliability. So let's go back to our scenario where things are wearing out. Where things tend to wear out when the system is slowly accumulating damage or otherwise degrading. That is, there is an age component to it. So things like fatigue cracking, corrosion, wear, contaminants in lubricants, those sorts of things. Those are examples of failure mechanisms that involve damage being accumulated with usage. So every mile, every hour, or every cycle you operate your system, it doesn't make the system fail necessarily, but it introduces damage that makes failure more likely. So if I know this, I can start targeting my redesign efforts in a particular way. If we know which failure mechanism it is, we can introduce more robust components. We can potentially introduce preventive maintenance or servicing. We can also reduce stresses. In short, we're approaching the problem of poor reliability in a very scientific way. Conversely, if failure patterns failure tendency looks like this, where we see wear in or this cluster of failures at the start of usage, which then becomes less and less frequent, we are likely looking at manufacturing defects. The reason why is because every time you fix something, you're potentially removing a manufacturing defect if that failure was caused by that manufacturing defect. And if you have manufacturing defects, then what you will likely see is failures occur often. And so if in this process where these failures are occurring often and early, you're actually improving the design of the configuration of the system by fixing it and repairing it and removing that manufacturing defect, you tend to see a decreasing hazard rate or wear-in/infant mortality. And if you see a constantly occurring rate of failure, then what we are looking at, what the root cause is likely going to be, is something related to external events. Think lightning strikes, think human error. It doesn't matter how old or how young the system is, these things, when they do come along, are causing the system to fail. A classic example is voltage spikes in electronic componentry. So what that means is that if I see this particular failure pattern, what I'm going to look for is, if it's mechanical, some sort of protective cage, or some look at how the human operators use this particular system. If it's electronic, I'll be looking at dirty power supplies, so on and so forth. But the key thing is, I now am informed in regard to moving forward and how to make my system more reliable, which is why we're here. So come back to what a reliability engineer is supposed to do, not admire the problem. What am I here to do? I'm here to improve the design and make it more reliable. That's what a reliability engineer is here to do, nothing else. All that other stuff is just a path to making a more reliable system. If you're admiring a problem, it's not helping. So for me to be able to do this, I need to know the nature of failure. And if you tell me that the MTBF is equal to 12.5, that tells me nothing about the nature of failure. So if there are any questions, please feel free to log them, put them into the chat window. I'm going to ask Fred to interrupt me if any good ones come along, and we can address them as they happen. But hopefully you understand that if you tell me as a reliability engineer who wants to improve the MTBF, improve the reliability, if you just tell me the MTBF is 12.5, I need to essentially go and relook at all the data, reanalyze the data to try and understand the nature of failure. And to understand why the MTBF is much, much worse than this very simple shortcoming in terms of the information it contains, we now need to look at something else. So let's talk about probability density functions. And there's a chance that many of you out there already know what a probability density function is, or PDF. A probability density function / PDF gives me the probability that a continuous random variable is equal to a specific value. Now, we have to sort of talk about PDFs if we want to truly understand how terrible MTBFs are. So I'm not trying to torture anyone by introducing an additional concept. We really need to talk about PDFs if we want to know why we should never use the MTBF for any reliability application. Now, if you've never heard of a PDF before, there is a chance that you have heard of what we call the bell curve. Now, a bell curve is a form of PDF. And here is an example PDF which looks a little bit like the bell curve, but it's not quite. But it gives us a feeling about the random nature of a particular variable. So in this case, if you look at the horizontal axis, you can see that the peak of this sort of wonky bell is around about 2, which tells me that the most likely value that our random variable is going to take is 2. Now, the area under this PDF must be equal to 1, which is simply just a way of saying that all possible values must have their probability sum to 1. And if we want to work out the probability that a random variable lies between two values, such as 2 and 6, we simply find the area under the PDF between those two boundary numbers, or those two limits. Now, that is the extent to which I'm going to ask you to jump into probability theory. If you can understand this, then you'll have enough knowledge to be able to keep up with me for the rest of this webinar, because we're going to look at an example now. Now, this example is based on a particular type of failure, specifically wear out. So here is our axes, and we're going to put on these axes this wonderful bell curve, which I referred to before. A bell curve is a thing that we often, is a PDF shape, which we tend to think about as our default understanding of random nature, because it has this nice symmetrical property. It sort of looks like it's most likely around the value we think is the most likely. And all those things just feel right about the shape. You can see that the random variable value is more likely to occur in the middle, or the hump of this bell, and less likely to occur in what we call the tails. And because most of the random variables occur away from 0, we can say that this is what the PDF looks like when it describes wear out failures, specifically the time to failure for systems that wear out. Because the system fails typically around about a value which is a long way from 0, we know that this is a wear-out system. So straight away, we can make some interesting conclusions. But let's not get too fixated on this beautiful bell curve, because we don't see it all the time. Let's change it. And we're going to change this bell curve in a particular way. I'm going to add this little scale or gauge on the right-hand side. And at the top of this gauge or scale represents wear-out. The bottom of this scale or gauge represents infant mortality, or wear-in, and this black line in the middle represents a constant hazard rate. That is a system which doesn't age, it doesn't wear in, doesn't wear out. Now we're going to put that little arrow at the top, and let's see what happens when we morph or change this probability density function. And this is where the animation may or may not come through very well. So you can see that our bell curve, for those who can, is slowly moving towards the vertical axis. And then it sort of touches a vertical axis and then it shoots to the sky. Now, for those of you who are looking at the scale on the right, you can see that our little arrow move from the top all the way down to the bottom. So this PDF shows what happens if we move from an exclusively or extreme case of wear out to an extreme case of wear in. That's what it looks like. And now most of the random variables occur close to zero. That should make sense, because when things wear in, they have, what we're saying or suggesting is that they are occurring, failures are occurring early. So we see our random variable values occur close to zero. But one thing about every single one of those curves was that one characteristic that was held constant was they had the same MTBF or mean. What that meant was that bell curve, as it was morphing towards that weird sort of clingy PDF curve which hugs the vertical axis, every single one of those transition probability density functions had the same mean. And we're going to explore that in greater detail. So we're going to look at go back to our bell curve. Here is the MTBF if our bell curve describes time to failure of an extreme wear out system. And we know from our little introduction on PDS that we can see, due to symmetry, that about half of our systems will have failed by the MTBF. Now, for some of the audience, this might be revolutionary in terms of understanding what the MTBF is all about. The MTBF is cannot be used as a proxy for failure-free periods, far from it. Based on this PDF, we can conclude or see that half of our systems will have failed by the mean time between failure, which is not a scenario that any organisation, user or customer actually cares about. They typically only want to know, when the systems are going to typically operate without failures, which means we're interested in a value which is much less than the MTBF, because by the time half your systems have failed, it is now economically too late for anything to be done about it. So the area under the PDF, before the MTBF is 0.5. So in the cases of extreme wear out, we expect 50% of failures to occur before the MTBF. So just remember that. So let's see what happens if we do the same little morphing animation or morphing transformation. So let's see what happens to that figure. How many things do we expect to have failed by the MTBF if we transition from a wear out scenario to a wear in scenario? So again, hopefully the animations will come through. Yeah. Add our little gauge on the right hand side, and for those of you who missed it the first time, the little arrow at the top will move down to show you how we are tracking towards infant mortality as this PDF morphs. Now you can see that as we start to wear in, the percentage of things that we expect to have failed by the MTBF increases. Keeps going and keeps going and keeps going and keeps going. And actually, statistically, that figure, the percentage of things that will have failed by the MTBF, will keep going up until, but not quite reaching 100%, as we make our system experience more extreme wear in. So how is this possible? Well, what we're seeing here is essentially the few failures that occur beyond the MTBF are so far to the right that they essentially balance out the overwhelming majority of failures that occur before the MTBF. So it might not feel right, it might not sound right, but yes, we expect almost 100% of things to have failed by the MTBF in the most extreme case of wear in. And statistically, that does not intuitively make sense to us human beings. And that is the main problem with the MTBF. Anywhere between 50 and 100% of failures will occur before the MTBF. That is a fact you cannot escape. And there are no scenarios that I've ever come across, and Fred, and I'm sure that many of the listeners to this webinar would agree with me, there's not many companies or organizations or customers or users or clients actually are interested in a point where the majority of their systems have failed. They want to know when the majority of their systems are working. And when we mean majority, we're talking about 90+%. So this metric is somewhat meaningless. And if you just give me the MTBF, and I do not know as a reliability engineer the extent to which it's wearing out or wearing in, then I certainly can't tell you what this figure will be. All I can tell you is that it's going to be somewhere between 50 and 100%. Now, for those of you out there who use a constant hazard rate or assume a constant hazard rate, which one of these PDFs that as we were morphing from wear out to wear in had the constant hazard rate? Well, it was this one here. And in this, where we assume a constant hazard rate where things never wear out or never wear in, we see almost 2/3 of our systems failing by the MTBF. Again, if you give me the MTBF, I have but no choice but to assume the exponential distribution, which this is, because the exponential distribution is the only distribution I have where it only needs one metric or one parameter. What is that parameter? The MTBF. So I may have jumped ahead a little bit here, but the exponential distribution. The exponential distribution is based on a very simple statistical or probabilistic process, but it helps us measure time to or between events for a constant hazard rate. So the exponent itself is a number that denotes the power to which another number is raised. In this case, you can see x to the power of a, where a is the exponent to which x is raised. Now, so for every unit increase in x, the value of x to the power of a will increase by a factor of x. So increase by a factor of a. Noting that if a is negative, x to the power of a will go down by a factor of a. So I can see a few questions, I might hold it right there. I can see a few questions coming through right now. I see that William is asking the 50 to 100% is if the 50 to 100% is applicable if the bell curve is centered, what happens if it is skewed to the right? Now, I think that the question that's being asked here is if if we see a curve where it has a long left-hand tail, but the bell curve is sort of squished to the right in terms of shape. And statistically, that's true. If you have a curve or a PDF which has a long left-hand tail but is skewed to the right, then you will see fewer failures occur before the MTBF. The problem is that curve where you see a long left-hand tail skewed to the right rarely occurs for a time to failure. The reason being is because what you're looking at is typically a logarithmic wear-out pattern. We can go into statistics later on, but that logarithmic wear-out pattern acts the other way. It has a multiplicative effect. So you see that sort of skewed bell curve with a long right-hand tail, and the bell part is skewed to the left. I don't think I've ever seen a scenario where you actually see a bell curve skewed to the right with a long left-hand tail. So in the most extreme case of wear-out, what happens is essentially you see this increasingly bell-like shape, which is beautiful and symmetric. Think your vehicle tires wearing out over a large distance. As failure occurs a long way away from zero, you typically only ever see the bell curve. You don't ever see those PDFs which have those shapes where you can statistically or probabilistically get fewer than 50% of things failing before the MTBF. It just doesn't happen in reliability for a number of reasons. So going back to the exponential distribution, sorry for jumping back, but if we look at the height of our curve here, you can see that for every unit increase in time, usage, or duration, you see the same percentage decrease. That means in this case, your curve will decrease by a factor of 2 for every uniform step moving forward. And this means it decreases at a constant rate with respect to x. This is what constant hazard rates are all about. So this can become our reliability curve, where this curve starts at 1 and approaches 0. This is what it looks like if you have that constant hazard rate. In this case, our hazard rate is 0.1 failures per unit duration, which means the MTBF is 10. So an observation. The exponential distribution can be used to model failure where the probability of failure does not change with respect to time or usage. There is no scope for wear in or wear out. And because it is simple, it only requires one metric or one parameter, it is often used to reduce complexity. Now, the reason why we're talking about the exponential distribution is because it is the only, because we see it in so many textbooks, and the reason we do is because it is simple, and these textbooks were written before we had computers, before we had calculators and things like that. So the reliability engineers of the 60s and the 70s had to use these assumptions, otherwise they couldn't make any conclusions about the data they were analysing. But we've moved on. We have Excel on all our computers. We have calculators. We have all these things that allow us to move beyond a simple assumption that the system we are modelling has a constant hazard rate, but our textbooks haven't moved on, and that is a problem. So if we come back to some very common mistakes people are making about failure in MTBFs. And before we do that, I can see there's another couple of questions being asked. I can see that Caitlin is asking, the MTBF is a mean average. How can 100% of failures occur before that value? That's a good question, Caitlin. And what we're trying to say here is what is actually happening is, as things increasingly wear in, the percentage of things we expect to have failed before the MTBF increases, because the few that occur beyond the MTBF occur so far beyond the MTBF, those 1 or 2 or 3% tend to balance out the overwhelming majority that happen before the MTBF, because they occur so far beyond the MTBF. It's like a seesaw. If you're a heavier person, you sit closer to the fulcrum or the balance point of the seesaw. If you're a lighter person, you can balance the torques or the moments by sitting further and further away. So it's not possible for every single random variable to occur before the mean, but statistically speaking, that is a limiting effect of changing a system from an exclusively wear out to an extreme wear in. It will only ever approach 100%, it will never quite get there. So let's go back to some common mistakes people make about failure in MTBF. The first thing that when people think of when they hear a mean of something, if I say, look, the mean of this process, the mean height of this population of people, or the mean speed of that vehicle is this particular value, we don't think, or we don't characterize the uncertainty in our head using this exponential curve you can see on the screen. What human beings tend to do is think of the bell curve. If you tell me the mean of any process is 12, in my human head, which is not really designed to process probability or statistics very well, I think that 12 is some sort of central or typical or representative value, and it's also the most likely value. And while I'm not absolutely certain that that random variable has a value of 12, I believe in my head that when you tell me the mean is 12, that the real value is somewhere near 12, and that's classic bell curve behavior. Problem is, if you tell me the mean of something, it might not have this beautiful bell curve describing the random process, but that's what we as human beings tend to think about, and that's the first problem. The mean time between, in this case, the mean time between failure for a scenario where we expect to see failure occur around about 12 is 12 as represented on this chart. But it gets a lot worse than this. So I dare say there's a number of people out there who have been in workshops or design review teams or committees or reliability centered maintenance workshops where it comes time to talk about servicing intervals. When should we conduct preventive maintenance so that our system doesn't fail? And someone will invariably go to the OEM data and say, well, this thing that we need to swap out, the oil, the gasket, whatever it is we need to touch, they say the MTBF is 12, therefore the preventive maintenance interval should be 12. Well, that's going to get you into trouble, because if you say that the MTBF, sorry, if the servicing interval is 12, what you're actually wanting to describe, or what you are actually describing, is a scenario where the duration of 12 hours, kilometers, miles, months, what have you, is roughly the failure-free period, or the period in which you would expect very few failures to occur. And so for this to happen, if we have a bell curve, which describes our the true time to failure, the mean time between failure needs to be much higher. In this case, closer to 20. But if you said the mean time, if you said the servicing interval was 12 for this scenario, what does that mean? It means that half your systems will have failed before you service it, which means you'll have an unhappy customer, you'll have an unhappy operator, and you'll have an unhappy design team, because everyone thinks they're doing everything correctly, but we're still seeing half of our systems fail before they get serviced. And that's a problem. But this happens over and over again. So one lesson I'd ask everyone here to walk away with is, don't ever think the MTBF is equivalent to a failure-free period. And most people will say, yeah, I get that, but you'd be amazed how many smart people, and I do mean smart people, I've seen just say, look, the MTBF is 12, therefore the servicing interval needs to be 12, move on. And that causes millions upon millions of dollars of damages later on. So if you're a reliability engineer and you understand this, then it's up to you to make sure that your managers, your bosses, and your leaders also understand this as well. But we're going to go on to another field of reliability or probability or statistics, where we can also make substantial errors or substantial mistakes because we think we understand more than we do about a particular problem. So, for example, let's consider a fleet size problem, where we're now in a transportation company which has 8 trucks, needs to have 8 trucks available all the time. And they, in this case, know that the trucks that are available to them are available 80% of the time. That is, if you go up to any one of these, there's an 80% chance that it will be working. So all we need to do to ensure that we have 8 trucks available all the time is to have a fleet size of 10. Is that right? Well, let's see. Without going into the details, we can apply some principles of probability and statistics and create this little chart here. And these little columns give us the probability that we will have a certain number of trucks available at any one point in time if we have a fleet of 10 and their availability is 80%. And you can see here that there is a 68% chance of having 8 or more trucks available. Now you remember, the company needed to have 8 trucks available all the time. Now in this case, sometimes we'll have 9, sometimes we'll have 10. But there is going to be a 32% chance that they don't have the 8 trucks they need. And that means that one day out of every 3, they can't make money, or whatever it is they do to make profit. So whatever it is they need to do to make profit. All because of a simple probabilistic assumption that because the availability is 80%, we need 8 trucks, therefore we need a fleet size of 10. If you do this math, you follow the theory, you need to increase the fleet size to 14 to have around about a 1% chance of having 8 or more trucks available. But you'll never ever get to a state where you can say, I'm 100% confident that all 8 trucks will be available. You can increase the fleet size to astronomically high numbers, and there's still a finite chance you won't ever have 8 available. This is another common error. So we need to understand what our risk tolerance is. Okay. So enough of this nonsense regarding probabilistics and statistics, probability and statistics. It's very, very boring. So let's just say a number of you, so a fraction of you are a boss or a manager or a leader, and this seems to resonate with you. What do you need to do to be able to do something about the MTBF and its disastrous consequences if you assume that to be a metric that matters? Or how about we put it this way? What could happen if you're a boss and you focus on the wrong metric, period? Might not be the MTBF, you might be focusing on things that seem to make sense to you, but by rewarding those metrics, you actually introduce the behavior you're trying to avoid. So let's look at an organization where in this in this scenario, the boss tells his staff or her staff how important reliability is. So they have posters on the wall which say reliability is their number one priority. We then have reliability hero of the month. And what that means is that they have, what I'm talking about here is they have these awards or certificates or public announcements of excellence where people who are perceived to be doing a good job in reliability or quality or due diligence, whatever the case might be, get some sort of recognition. And the bosses might think, well, I'm actually using positive affirmation to reward good behaviour. So surely my products will now be reliable as well. But in this scenario, the boss also provides bonuses to staff who are on budget and who are on schedule. Now, being on budget and being on schedule is very, very important. So this surely makes sense. You want to reward people who are on budget and are on schedule. So let's see what happens. So let's look at engineer number one, who focuses on schedule and focuses on budget. So they meet budget, they meet schedule, compared to engineer number two. Now this engineer who saw that there is posters up on the wall saying reliability is our number one priority, wants to be the reliability hero of the month, he or she does some reliability stuff, and schedule increases by 2% and budget increases by $150,000, or perhaps more correctly, she goes over budget by $150,000. But the reason she did it was because she could work out that by fixing problems now, she saves $2 million later. And in reality, we'd see huge orders of magnitude. We should see huge return on investment for this sort of for these sort of figures. Where if I was investing $150,000 and making my product more reliable during the design space or design phase, I would typically expect to see substantially more than $2 million saved later. And the reason why is because defects and customer problems are extraordinarily expensive to fix compared to the simple design change you could have implemented years ago. But engineer number one is the one who gets the bonus. And because the manager, if you're the manager and you say, I'm going to reward people based on schedule and budget, this is the behavior you're actually rewarding. It's not just you're not rewarding people you are rewarding people who get certificates and get the Heroes of the Month award, but you're communicating to your organization what behavior you really value. And because you really value schedule and budget, you give bonuses accordingly. Certificates are cheap, posters are cheap. If you're going to give out bonuses and do things like give promotions, then you're telling your team what sort of behavior it is you value. Now, this person over here who sees this sort of behavior will quickly realize that it's irrational for them to keep doing this stuff. It is irrational for them to be over budget and increase schedule by 2%, even if it's good for the company. So what that means is, as an organization, by rewarding the first sort of behavior you see is when engineers see opportunities to save your company almost $10 million, they simply walk by. What will most likely happen for the truly high performers is they'll simply leave your organization and work in another organization where that sort of behavior is rewarded. So if your job as a boss your job is not to check your engineers' work because you should have already hired smart people. Beyond that, you should be understanding what it is you need to reward. Is it MTBF? Is it budget? Is it schedule? If you reward one type of metric, one type of performance criterion, without thinking it through, if it doesn't universally apply, you will almost certainly hurt your prospects in other areas. Your job as a boss is not to check your engineers' work. You should have already hired the smart people. Your job is to provide guidance, motivation, competence, and capability and resources. Guidance means clear goals related to profit, not MTBF necessarily. Not MTBF, not MTBF ever. It's not necessarily strictly budget and schedule. You need to motivate people. You need to reward them. You need to incentivize them. You need to give them resources to do testing. You need to train them. You need to invest in them. And as discussed, you should have the right metric, not the MTBF, not schedule by itself, not budget by itself. You should be trying to let your smart people in your organisation know what it is you value, and let them work out how to get there for you. So if you're still not convinced, because I don't care how reliable it is for the customer, all I need is my equipment developed fast and cheap, because that's all I get. That is how I get assessed as a leader, as a designer, as a design lead. Have a look at this example. In this example, we're going to look at a common or traditional design process, where that little red bump there represents design effort with respect to time. So the vertical axis is cost per unit time, and the horizontal axis is design time. So that area represents how much effort over time we're investing into designing a thing. And this little area here represents engineering support. This big area here represents eliminating failure modes and mechanisms, and the last bit over here represents certification. So this is a common design process where if we focus on designing something that can work up front as quickly as possible, we need to spend a lot of time afterwards after testing or identifying defects, and then working out what it is we need to do to update that design at typically great cost and delay. Now, all this needs to occur before launch. After we've done all these things, we then launch our product. This is all about time to market. So let's compare this to a more robust or more advanced design process. You can see that all the things are still there that we just talked about, but in different quantities. And in this scenario, launch has been brought forward. Now let's look at these little lines in greater detail. You can see the common traditional approach up the top right-hand side, where you see we didn't invest a lot of time into design. And the bottom left-hand side, where we invested twice as much effort. What were we doing? We were using a scientific approach to failure. That is, we were trying to model, we were trying to analyze, we were trying to interrogate our design before it got to the prototype stage. So we were designing out root causes before they even became a thing. And that means we didn't have to stumble upon failure modes and mechanisms during development, which means we didn't have to spend as much money on engineering support or certification. And the development time was halved, all because we had a scientific approach to failure. We thought about how the thing could fail before we started design and during design. Now, this is what we call a robust design process that scientifically analyzes the way components can fail as early as possible. And this is, to be honest, design, test, fix, relies on finding failures once we get to the prototype stage. Now, these aren't random lines that I've just drawn on a screen. No, these are the results of an academic study into the design and development of a liquid rocket engine for space applications. So these are genuine, or let's just say scientifically derived lines that represent the amount of effort that goes into designing products when you're using a common or traditional approach versus a robust scientific approach. So these aren't just random lines. This is a true representation of how introducing a robust design process in liquid rocket engine designs for space applications can rapidly or can accelerate development, reduce development costs before it even leaves the factory. Now, we've seen, obviously these curves will change from industry to industry, but the principle remains the same. We typically see substantial reductions in schedule and substantial reductions in cost if we take failure seriously, if we have a scientific approach that we implement up front. So, returning to Hewlett-Packard, many of us reliability engineers do what's called a DFR survey, Design for Reliability Survey, and Hewlett-Packard was one of the first organisations to really take this seriously. And a DFR survey is a semi-subjective, semi-objective assessment that reliability engineers make regarding the culture of an organisation. Myself or another reliability engineer will go into an organisation, we ask a bunch of questions to a bunch of different people based on different areas, and we give a score or rating for each question or each area from 0 to 4. And we tabulate these scores and we come up with a percentage value where 100% is great and 0% is terrible. Now, if we plot our DFR survey score on the horizontal axis of a chart, and we take all of Hewlett-Packard's DFR survey results, we get this relationship with respect to warranty per year. The percentage, you can see that we have warranty expressed as percentage per year on the vertical axis on the left in red. As Hewlett-Packard's divisions were improving, becoming more proficient at reliability engineering, their warranty rates, their failure rates were going down, and it's a very clear trend. But perhaps even more importantly, as their reliability maturity improved, their operating profit improved. Now, I suggest that if you could create an organisation which had in excess of 20% operating profit, your shareholders would be very, very, very happy. So you can just see here has a very tangible relationship between money, profit, value, and reliability. And what Hewlett-Packard didn't do was focus on the wrong metrics, such as MTBF. So, do not use the MTBF. Under no circumstances should you use it as a reliability engineer, because you need to seek to understand the nature of the probability distribution before making any important decision. And there are lots of other things we can use out there, such as the Weibull distribution, which is, we're not going to go into that probability distribution today, but into that probability distribution. It is a distribution which goes well. Distribution is wide, the exponential distribution, and it can characterize the nature of failure. I would cater to manufacture as a reliability engineer if things are wearing out, or have a constant hazard rate before I go and start improving the design of the system. So on that note, are there any questions, which I'll ask anyone to offer through the chat window?
I would just say don't use MTBF.
I have probably missed a few. Fred, you can jump in if there's any good questions I have missed, or
one of the questions that might get buried in a number of people typing is having you come back to talk about fit or Weibull or other things like that. If you've got the time in your schedule, I think you've got an audience here.
Mm-hmm.
One question was, it's different than that. It's similar to MTBF, some of the issues, but it's different. And I think it's more general question is, would you be willing to come back and do some more webinars here at Ascenda?
Okay, so fit, are you talking about failures in time, the sort of failures per 10 to 9 hours?
So there's a question.
Absolutely, and I think, correct me if I'm wrong, Fred, but the question about fits for those listeners in the electronic componentry industry where everything is about fits.
How about metrics like that?
Which is essentially a form of failure rate, which is the inverse of the MTBF. So we're talking about the same thing if we're talking about fits. Yeah. Yeah, so I think, sorry, I was half reading a question, a comment from Nelson. I've heard that BX could be used instead of MTBF. BX is that what you're talking about, Fred?
That's right, and it gets to the issue with MTBF is at the mean.
I suppose it comes back to what it is you're trying to do.
It's at the early tail. Usually it's B1 or B5
I assume
or B10.
Again, you're talking about the time by which you expect a certain percentage of things to have failed. Is that correct?
Yeah. It's 90%. Yeah. That's right. So I'm going to go back up to Arun's question, right? You see his?
Which is essentially a reliability metric. Because if you say B10, what's a B10 time, or time to B10? That's the time by which you expect the reliability to be 90%. So it counts reliability. Yep. Yes. Now, I must confess that I'm a bit of a rookie in terms of Adobe Connect, so I've been looking at 3 separate screens trying to keep my train of thought. So I haven't been able to get up to speed. But so I think the key part that Arun says is truck oil change goal can be set as 5,000 miles MTBF. And there's an interval between services, which I want to be very clear is actually very different to MTBF.
Yeah, I agree.
I think what Arun you're saying is it comes back to this whole BX thing is what is your servicing interval such that you expect an acceptably small percentage of failures to have occurred, which I agree with if that's what's being asked.
Annualized failure rate or annual failure rate. I know that HP used annualized failure rates oftentimes, and they actually even normalized it between the very expensive products and very inexpensive products as a weighted care across divisions. It was used because it was accessible. As we got deeper into the analysis at HP, and this was after the time that Chris, you were talking about, is then we started using more Weibull distributions directly in order to describe the time to failure patterns that we were seeing for different products. AFR it's different. It's more like a failure rate, and it's annualized, so that you can talk about a 3-month or a year or 2 years and make comparisons. But it's still a point estimate.
Which can be used, but again, it's a valid point. You raised it's a point estimate. So if you've got a capability or a system or a device which is going to last 20 years, the average failure rate for a particular year or an annualized failure rate is essentially a snapshot of the hazard rate at that point in time. So if you plot those out, you actually see a changing failure rate with respect to usage. So it's not assuming that it's constant over the entire life of the system, which means that actually not assuming it's constant at all.
Good point. No, I think
comparing it from year to year.
Zubin's question is
so even things that sound like
they're
talking about the failure rate,
because
in many cases,
Zubin, I don't really believe
about actually a genuinely valid observation.
It's easier to interpret in many
reliability
ways.
characteristics.
Easier to interpret correctly than just providing an MTBF for failure or an annualized failure rate. And maybe we can get Chris back to clear that up for you.
And I think
I have found that even managers can understand a Weibull plot, a cumulative distribution.
Plotting, not in a boring,
whereas if you give them just an MTBF value,
but actually go through what happens.
They think they know what it is, which is worse than
understand what it is
you don't know what it is.
I think that could be very useful given some of the questions.
Right.
Yes, absolutely. If at least that's a very useful thing to have, is you know where your limits are.
So by a little bit, I'll read it because
if you don't know where your limits are, then you're dangerous.
MTBF is not a really good measure of reliability,
but there's a ton of questions coming through, which I realise I certainly haven't been able to keep up
without it.
It
is the input to reliability analysis.
Rehearse, make mine. I'm going to have to disagree with that. So, for example, I've done plenty of reliability analysis where I've got field data or test data, and you can use any sort of, you can use Weibull distributions, you can use non-homogeneous Poisson processes, whatever process that makes analysis approach that works, and the MTBF does not form any meaningful.
There's one for any plans to get a hard copy of your book out there. So
from a Weibull distribution,
if you take a look at that book, it's
you
got,
don't have
I don't
to
know, Chris, how many on Kindle? It's
find the MTBF.
if you printed it, it would be a very, very large
which
book.
Best fits your data.
I think
so I'm not entirely sure.
It up into maybe 3 volumes to make it more viable as a hard copy. There's a
Yep.
All right. Well, thanks. Appreciate it.
But yeah, and so and answer the question from Brian, are there any plans to make a hard copy version of the book? The answer is absolutely yes. Now the plan is to find the time to do that. I'm about halfway through that project, but yes, I'm certainly trying to do that.